So the second part of this, the power lesson, talks about efficiency of energy transfer. So what is the efficiency level of that power? So we talked about the bouncing golf ball earlier when we were talking about conservation of energy. And in the perfect world, if there was 100% transfer, we would have the bouncing ball returning to its original height. However, not true, because we have sound and heat transfers. So the law of conservation of energy says energy can't be created or destroyed. It can be transferred into unexpected or undesired forms, and usually heat is the most common undesired form. When you look around stores selling common household items, there is what we call the Canadian Efficiency Guideline, and it tells you how efficient a particular household appliance is. So how are they calculating that mechanical efficiency? Well, first of all, the definition of mechanical efficiency is the percent of useful energy resulting from the total energy input for the system. So, formula, mechanical energy equals, or mechanical efficiency equals, useful energy divided by input energy. And then because it's a percentage, we multiply by 100. So there we go. So useful, that's how much is actually something that produces what we want. Okay, so think about that one. What we want and what we gave. All right. So a couple of examples with that. What is the efficiency of the 100 kilogram person to climb the stairs if they really used 25,000 joules? So 25,000 joules. So remember, it was 19,620 is what was actually needed to go up the stairs. Where did that extra joules come from? Well, how about you pause the video and run up and down your stairs for a second? What happens? Your body heat rises because you're exercising. Okay, not actually a bad idea if you want. Pause the video and go for a jog. But anyway, as your heat energy, as your body gets warmer because you're working, that heat energy is undesirable. Okay, you're actually expending chemical energy to move your body, but you're creating a heat energy. So you're losing energy within your body as well to undesirable means. So what is the mechanical efficiency then of the person running up the stairs? Well, useful over input multiplied by 100. 19,620 divided by 25,000 times 100. When you calculate that out, that gives you your percent efficiency. So 19,620 divided by 25,000 times 100. So you got 78.5% efficiency. And I would say that's fairly high for the average person, but you can check that with your phys ed teachers. So therefore, 78.5% efficiency. All right. Now let's talk about something that's, I'm not going to say more practical, but just as important. A light bulb is 10% efficient, and I am talking about your traditional light bulb that looks like this. So I'm going to draw it down here as best I can. So it's these ones. So in a couple of years when you're watching this video, and that's an absolutely horrible picture of it. It's that bulb shape that we're somewhat used to. Now in a couple of years, these bulbs aren't going to be available anyway. However, that's the bulb I'm talking about. 10% efficient. What does that mean? It means that 10% of the input power is converted to light. And remember, that's what the desirable effect of a light bulb is. I don't put a light bulb in my room to warm me up. Okay? I don't want it for sound. I want it for light. So 10% of what you put into that light bulb is useful energy. So A part, how much energy is actually provided? So A, how much energy is actually provided to a 100-watt light bulb in 60 seconds? Well, I know I've been given, in this case, power, 100 watts. So I know my power. I'll just use P. So power equals, I have 100 watts. I know my time is 60 seconds. So I know that it's only 10% efficient. So using our formula for efficiency, mechanical efficiency equals useful over input times 100. So 10% is equal to, what was useful was 10%. So, so then when I wanted to do that calculation, I gotta figure out how much energy was actually involved here. So I know I'm gonna go over here and make a side calculation. Power equals work over time. So I know the amount of power was 100 watts. I know the energy is what I'm looking for in 60 seconds. So yeah, I can leave it as a W. So my work energy here is 6 with 3 zeros, so 6,000 joules. Okay, but that's to produce 100 watts of light. Okay, so what that means is that was how much was actually useful. It's not how much I actually input. So I'm looking for that input times 100. So we end up with 6,000 divided by 0.1, and I get the input was 10 times that, obviously, because you had 10%. So we put 60,000 joules, therefore 60,000 joules to get 100 watts of light. Okay, to get 100 watts of light. So the 100 watt light bulb that you're putting into your lamp in your room, okay, you're only using 10% of the energy in there. What would the effective light power be from a 100 watt light bulb? So I think I maybe went about this a little bit wrong when I was doing my calculations, but what happens if, what happens is that when you do 100 watts, what's the effective light power? So I'll do this the other way then. So assume input power was 100 watts. So let's look at it the other way. Let's say that the light bulb received 100 watts of power. So what is the effective light power here? Well, we know it's 10% mechanical efficiency. So if I go back to this formula for a second, so useful over input, and I can switch it to in terms of power here as well. I know it's 10% mechanical efficiency, useful over 100 watts times 100. So useful, the 100s would actually cancel here. Useful is 10 watts of energy, okay, which if we use our power formula, W over delta T, so 10 watts equals times 60 seconds, 1 minute, 600 joules of energy. Okay. So I did the two questions a little bit differently, but you're really only using 10% of what's efficient there, or what's provided. Now, when you get these high efficiency light bulbs now, which are significantly different, you'll see you go to the store and those are the swirly bulbs, like the ice cream cone. So something like this. Let's see if I can finish this off somehow. So it comes around. Okay. So your swirly bulbs, those swirly bulbs, if you look on the boxes, they'll go, okay, 23 watt bulb is the equivalent of the old 100 watt bulb. Okay, so you'll notice that they're using a significant lot less power to get the same energy. So 23 watts to get 600 joules of light energy. Oops. Light energy, which we just calculated here. Okay, so that 23 watts, so much more efficient, the swirly bulbs, and that's why we're going to what these CFLs are. Okay, they're talking about when you get that reduction in energy. If you look at the comparison, 23 watts compared to the 100 watts, you're looking at, if you do the math, and it depends on the price of electricity at that given point in time, but you're saving something like $4, okay, per bulb. And I'm not sure. I think it's each year is what the claim is here. Go look on the box, but fairly significant, and that's why we're moving away from one to the other. And also, in terms of lifetime, for those that haven't looked into these light bulbs before, I'm going on a tangent here, but the 100 watt light bulb, okay, has a lifetime of, I think, I forget what exactly it is now. It kind of eludes me. I think it's like something like 100 hours or something like that. 100 to like 300 hours. Whereas this 23 watt light bulb, okay, will last something like 10,000 hours. Okay. So for example, in my house, 5 years ago, I put in all these CFLs in my house. I haven't changed a light bulb in 5 years. So it feels kind of weird when you have that. But so anyway, that formula, the mechanical efficiency formula, okay, is what you're going to be using in the second component of the homework. So at the bottom here, I have the homework from the textbook. If you have any questions, shouldn't have any. There's not that many questions there. You should be able to run through them fairly quickly. Please make sure you go through and try some of the questions, because some of them deal with pumps and moving water, and they're talking about per liter or per kilogram of water. So it's a good thing to try those individual questions. All right, good luck, and we'll talk to you in class.